So yay, here we are, beginning of our first new chapter. So chapter 13 is called Properties of Solutions. It is a great place to start in Gen Chem 2 because part of it is a review of chapter 11 from Gen Chem 1. There's also some review from other things in Gen Chem 1. Now this entire chapter is not 100% review. That's not true. But it does have review stuff in it, which means the entire chapter isn't brand new. So, like I said, I think it's a great place to start. Okay, so we're going to get into this we're not going to hit the math component of this chapter yet. This chapter kind of has, I consider it, three parts. The introduction background stuff, which is where we're at right now. Then we're going to get into the calculations that are definitions of concentration units. You're going to hear words like molarity that we've heard before. And then we're going to get to the colligative properties component. So we're doing three parts, and right now we're in the background part. So, beginning of every chapter this semester, I've got the list of the chapter objectives. Now, those are also on Canvas. The course objectives that are listed by chapter and also sorted by exam. What this is useful for is this tells you exactly what I expect you to learn and be able to do by the end of this chapter. So no one can tell me, I didn't know what to study for the test. I'm telling you right here what to study for the test. Now, no, it doesn't have the answers on it, but it tells you what you need to know and be able to do. Okay, so starting with chapter 13. First, a review of some vocab words you've heard before. The term solution is just a homogeneous or homogeneous, however you want to say that, mixture, which the definition of that is two or more pure substances that are put in the same container, and when they're mixed up, they're evenly mixed. Okay, so heterogeneous mixtures are the other type of mixtures, and a heterogeneous mixture, throughout the entire mixture, it's not evenly mixed. So like sand and water, when we mix those together, the sand sinks to the bottom and the water sits on top. That's a mixture because there's two things, sand and water, but it's a heterogeneous mixture. A homogeneous mixture would be where I mix the things together and they evenly mix. So if I take Kool-Aid mix and sugar and water and I put them all in the same container and I stir it up, once I stir it up, now I have a homogeneous mixture because theoretically the first glass out of the Kool-Aid pitcher and the last glass out of the Kool-Aid pitcher should taste the same because it's evenly mixed. With the sugar is evenly mixed, the color is evenly mixed, all the flavors, the other things in the Kool-Aid plus the water are all evenly mixed. So when we're dealing with a solution, which by the way, the solutions don't have to be mixed in water. Air is also a solution. Okay, so they can be gases, they can be liquids, they can be solids, they can be a mixture of those. But when we have a solution, we have at least one solute and exactly one solvent. So again, the mixture is made of two things. So the solvent is the one that there is the most of. So in the lab, often it's water, right? We mix something with water. In that example with Kool-Aid, the solvent in Kool-Aid is water because the thing there's the most of is water. Solutes are the other things. Okay, so if there's two things in the mixture, one of them is the solvent, the one that there's the most of, and then the other one is the solute. Well, if there's three things, there would be two solutes and one solvent. It's always going to work. There's only one solvent and there's multiple solutes if we have enough things for there to be multiples. The solvent is the one that there is the most of. Okay, so if we're taking two things and putting them together, and I want to know if they're going to make a solution, are they going to make a homogeneous mixture or are they going to make a heterogeneous mixture? Well, if they're going to make a homogeneous mixture, there are two factors that decide this. One is their natural tendency towards mixing, which is a very vague statement, but what we're going to look at is how heat, which is enthalpy, and disorder, which is entropy, and how those play into that. And then the other factor are the intermolecular forces. Now that is the thing that we learned in chapter 11 in Gen Chem 1. So if you took Gen Chem 1 somewhere else, or it's been a while, chapter 11 is your friend. I am going to review this, but I'm not going to review it with as much detail as the first time it was taught. Okay, and if you took Gen Chem 1 somewhere else or a really long time ago and you want some information on it, I have recorded lecture videos about chapter 11 that I'm happy to share with you. So we're going to start with our natural tendency towards mixing. We're going to look at, well, what does that mean? Okay, well, if we take two or more components and put them together, and then they mix spontaneously, that means without effort. Well, gases always mix spontaneously, which means they happen naturally on their own. Okay, because gases naturally fill the container. So if I put one gas in a container, it's going to expand and fill the entire container, evenly distributing itself. Now, one gas is not a mixture. But if I take a second gas and put it in the same container, it's going to automatically expand and fill the container and evenly distribute itself. So not even trying to, those two gases made a homogeneous mixture because they evenly spread themselves out in the whole container. And that's just following what a gas does. So if you take multiple gases and put them together, they will always spontaneously mix into a solution. Okay. But if we're looking at solids, liquids, or a combination of gases and liquids and solids, one thing that plays a role in this is the randomness of the molecules when it mixes. And that measure is entropy. Entropy is defined as the randomness or disorder of a system. So when we mix things, we're making it more random, okay, often. So, and entropy, it's the measure of this randomness. So in this example, we've got oxygen gas, which are the red spheres, and argon gas, which are the green ones, that initially are separated from each other. We put them in the same container, and they naturally mixed. And in doing so, we increased the entropy. We made it more disordered. It looks less organized when they're mixed together than it did when they were separated and in their own components. So, things becoming more disordered, more unorganized, more random, that property tends to go along with things making solutions. The way I think about this is making a solution naturally. It's like naturally going to mix. We don't have to force it by running electricity through it or heating it up or something, but I mix two things together and they naturally mix. For it to happen naturally, well, I think about naturally in my life and randomness and disorder. So disorder, if I'm going about my day, which one's more likely to happen naturally? Spilling something and making a mess, which would be increasing the disorder, or spilling something and it naturally falling into already organized piles. Thinking like laundry or something. Yeah, they don't typically, I mean ever in my experience, when I drop something, it does not naturally organize itself. So in a thinking about things being natural processes tend to become more messy. Okay, so things that happen naturally are typically more messy. Things that are going to become less messy, less unorganized, or more ordered. It's not that they're impossible, but they don't happen naturally. You have to put energy into it. If I want to, if I have my laundry and I throw it on the floor, it's naturally a mess everywhere. The socks are everywhere, underpants, pajamas, jeans, whatever. They're just everywhere, okay? But if I want to sort them into the loads that I'm going to put into the washing machine, that takes energy and effort on my part. That is not a naturally occurring process. That is a forced process, okay? So let's look at entropy and then remind ourselves of enthalpy, which is another thing from Gen Chem 1 that we would have learned, but that's the heat component. So enthalpy, that word, oops, need a Y there. The symbol for that is delta H. And as long as we're at constant pressure, enthalpy and heat are the same thing, okay? Now, when delta H, which is measuring heat, heat is a form of energy, so it can have a positive value or a negative value. Well, if the delta H value is greater than 0, which means it's positive, we have a word for that. It's called endothermic. That means it absorbs heat. Now, if I have a scenario where the delta H is less than 0, that means the number will be negative. That word is exothermic. And that means it releases heat. Okay. So we just talked about entropy. So this is more than we have to know right now in chapter 13. Well, not the thing that's more is that the symbol for entropy is delta S. Okay, but we will be dealing with that later in the semester. So entropy measures the disorder. Disorder, randomness, I'm just going to go with disorder. So delta S can be a positive or negative number as well. So if delta S is positive, that means the change in disorder is increasing. So it's becoming more disordered. And another way to say that is there's less order. Okay, well, delta S can also be less than 0, which is negative, which means the change in disorder is going down. So there's less disorder, or in other words, there is more order. Now with entropy, we don't have fancy, I don't know why I'm calling them fancy, but words that describe this, we just have these descriptions. Okay. So what I want us to do now, these are our definitions. I want us to look at enthalpy and decide which of these two scenarios we think is more likely to result in two components mixing to make a solution. So which one is true for something that will naturally mix? So if endothermic is something that needs to absorb heat and exothermic is something that needs to release heat, well, if we're trying to make it happen naturally, well, if something needs to absorb heat, it means you're going to have to give it heat, which means that process cannot or is less likely to happen naturally because you have to make the process occur by adding heat to it. So exothermic things are releasing heat. They can do that on their own. So if something's exothermic, it's more likely that that process, that whatever, is going to spontaneously make a solution. Those two components that I'm mixing together, if it's exothermic, it's more likely to spontaneously make a solution. Now, I already mentioned this, that the disorder increasing is more likely to make a mixture. So my little purple asterisk means spontaneously, well, I should reword this, more likely, because these are not absolutes, more likely to spontaneously make solutions. So if something is increasing in disorder, which is this one, and it's exothermic, which is this one, I could say absolutely it's going to make a solution. But if I have something that is endothermic over here and more disorder, I don't know for sure. One thing is kind of going for it, one thing's going against it, so we'd have to see. So what I want you to know out of this are these words, enthalpy, entropy, the words endothermic, exothermic, what they mean, the words more disorder, less disorder, more order, like these things, and then understanding which of them are more likely to show a spontaneous mixture. Okay, so knowing this chart and then where the asterisks are and what those asterisks mean. Okay, so looking at our enthalpy some more. Well, when we're trying to make a solution, again, let's just go with a simple one where I've got one solute and one solvent. In order to make the solution, well, I'm going to have to take the solute that's all in its own little container, like it's a little jar of sugar or something. In order to make a mixture, those sugar solute molecules are going to have to break away from each other. We're going to have to separate them because they're no longer going to be clumped together anymore when I make my solution. Instead, they're going to be evenly distributed. So we're going to have to separate our solute from our solute. They're going to have to rip apart whatever attraction forces there are between those solutes. Okay. Then I'm going to have to do the same thing for my solvent. Take my solvent and rip them apart. So if I got water, the waters are all attracted to each other, so they're clumping together. That's great, but now I've got to rip those apart so that way they aren't clumping together anymore and can now mix with something. Well, both of those processes are going to be endothermic, which means they're going to have to absorb energy. In other words, you have to put energy into it. Those on their own, they're already clumped. They're going to stay clumped unless they're being forced to be separated. So we're going to have to force to separate them. So I've broken apart the solutes from each other. Step one. Step two, I've broken apart the solvents from each other. Now what I'm going to do is put them together. When I put them together, the solvent and the solute that are now free to form new interactions are going to interact with each other. And this will be an exothermic process. Okay, because now we're putting things back together. Step one and step two are breaking things apart. So we're like breaking things. I don't know why I thought that looked like breaking things. And then breaking things and then putting together. Yeah, these symbols mean nothing. So this was breaking things. This was a break. And this is putting together. So this one is going to be positive energy, and negative energy. Okay, so if we look at that, well, when we're making a solution, all three of these things have to happen. So when I'm looking at, I don't want me to write on here anymore. When I'm looking at endothermic or exothermic, in order to make that determination, I would have to look at step one, step two, and step three and add them all together to see what the overall change was. So step one's positive, step two is positive, and step three is negative. Great, but what I need is the overall total. That's what I would be looking at to determine if it's endothermic or exothermic. Okay, so that's just some visuals to go with the three steps that I mentioned before. Okay, so looking at the energies, like trying to add step one, positive energy, to step two's positive energy, to step three's negative energy. I'm skipping forward here to this that's that situation. So here's step 1, and it's a positive arrow. It's going up. We'd have to add energy to it. Step 2, going up. Again, step 1 was taking the solutes and breaking them apart. Step 2 was taking the solvents and breaking them apart. And then step 3 is an arrow going down. So it's negative because we're putting the solute and the solvent together, and that's a good thing. So energy is being released. So what we'd be looking at in terms of deciding if looking at endothermic or exothermic, I'm looking at this difference. Like I added the 3 arrows together, and whatever I got when I added all 3 together, that's what tells me if it's endothermic or exothermic. Well, in this situation, where I started, which is here, and where I ended, which is here, well, the difference is a positive change. So this would be endothermic, which is less likely to be excuse me, spontaneously mixed. Sometimes when I mix these together, it's an exothermic, where the solution would be down here somewhere. What changes are the sizes of these 3 arrows, and those are unique to each situation. So this is just showing how we would determine if something is endothermic or exothermic by looking at these 3 steps. Okay. So this one, it's endothermic, okay? But turns out that the process that they use to make this graph is actually a spontaneously mixing process, which means it happens naturally. So what it is, it's ammonium nitrate and water. When I mix ammonium nitrate with water, it's endothermic, which means it absorbs heat. Okay, this is actually one of the sets of ingredients that are in those cold packs you can buy at like Walgreens, those little plastic baggy things where you smush them and then you put them on your skin because you've got a sore muscle or a headache or I don't know what. And then you put them on your skin and they make your skin cold, because what's happening is that package is absorbing the heat from your arm or your leg or your head or whatever. So it's absorbing the heat, which is what endothermic. But when I take that cold pack that I buy at Walgreens and I smush it up, which all that smushing it up is doing is adding the ammonium nitrate and the water and letting them mix. So it's making the mixture. I didn't have to do anything special to make it happen. All I had to do was introduce the ammonium nitrate to the water, which means it's spontaneous. But this is endothermic. Well, the reason why it ends up being spontaneous is it's a crap ton more entropy, or there's a lot more randomness or disorder to counterbalance the endothermic thing. So endothermic, exothermic is one piece that plays into whether or not something will happen spontaneously or naturally. The entropy, the increase or decrease of disorder, is a second component that goes into that. And then there's a third, which are the intermolecular forces. Okay, so in this chapter, I would not give you a situation and say, tell me absolutely with 100% certainty, will this and this mix together, by giving you if it's endothermic, exothermic, or increase in entropy or decrease in entropy. You can't tell the whole story from those 2 things, but you can tell what is most likely to happen. Just the fact that it's endothermic, I would say that's not very likely to be spontaneous. But then the fact that the entropy is it's going to be more disorder, well, that is likely to be spontaneous. So I've got a no and I've got a yes. So that's when you'd be like, I don't know, we'll have to try it and see what happens. Okay. So now we're to our third component. We talked about enthalpy, entropy, which together are the natural tendency towards mixing. And now we're going to look at the intermolecular forces. So these are the attractions between 2 molecules, whether they are 2 molecules of the same thing, like solute and solute, or solvent and solvent, or between 2 molecules that are different. It doesn't matter. These are the intermolecular forces. Intermolecular forces are shown visually by dotted lines. So all these red dots that you see, those are intermolecular forces. They are weaker than covalent bonds and ionic bonds, which were when you were drawing Lewis structures in Gen Chem 1, you drew things like this. Those are solid lines. Those are the covalent bonds. Those are stronger than these intermolecular forces, which is why these are represented by dotted lines. So, intramolecular forces, it's actually the term for ionic and covalent bonds. Also metallic bonds, but I don't care about those right now. So we're not looking at covalent and ionic bonds. I just wanted to point out like the relationship. So intermolecular forces are weaker than intramolecular forces. Okay. So there are 4 of these intermolecular forces, and they are in order right now from weakest to strongest. and they are in order that way. So the ion dipole force is the strongest and dispersion forces is the weakest. So we're going to go through these 4 forces, and then we're going to practice identifying intermolecular forces, and this is where chapter 11 is your friend, because this is when these were first learned. So I'm going to start at the weakest. I'm going to start at dispersion, which are actually officially called London dispersion forces. Okay, so London dispersion forces, they're the weakest intermolecular force. They are between everything. So you have 2 molecules. You don't have to think about it. They automatically have dispersion forces attracting between them. Okay, they're between everything, but they are not constant. So what I mean by that is they turn on and turn off and turn on and turn off. So there's a dispersion, oh, it disappeared. There's a dispersion, oh, it disappeared. So if I had something like a helium atom, that's the atom with the nucleus in the middle, and it's going to have 2 electrons, okay? Electrons are negative charges, right? They repel each other because they're the same charge. So the helium atom, or the helium atom with the 2 electrons in it, okay, those electrons are going to constantly mirror each other to stay as far away from each other as they possibly can, okay? But there's a chance that for a minute, both electrons could end up on the same side of the atom, okay? What that would do is take this atom, who's not polar at all, but give it a kind of negative side and a kind of positive side. The reason why it has a kind of negative side is all the electrons are on one side. So that side's more negative, and the other side doesn't have any electrons. All it feels is the positive the positive force from the nucleus. Well, if I have another helium atom hanging out, doing its thing, but there's electrons floating around, well, as soon as its neighbor has this negative side, its electrons are going to move away from it because they're going to repel it. So then that helium atom is, for a second, going to have a positive side and a negative side. Well, opposites attract. So right there, there's going to be attractive force between those 2 helium atoms. Now, helium atom naturally does not have a positive and negative side. That was a temporary thing that happened for a fraction of a second. And so for that fraction of a second, we see this force between them. Well, as soon as those electrons go back to their original place, they're away from each other, well, then that's going to go away. Well, then that's going to make this atom go back to its original way, and then this dispersion force disappears. Oops. Sorry, atom. So that's why I said it's not constant. It's intermittent. It turns on and turns off and turns on and turns off. Okay. Dispersion forces increase with these things. More electrons. The more electrons an atom has, the more likely this is to happen because there's more electrons. It's easier for them to not be evenly split throughout the atom. And that correlates directly with a higher molar mass. So molar mass, adding up the masses on the periodic table. So the bigger the molar mass correlates with more electrons. So everything has dispersion forces. Okay, if we're comparing dispersion forces of one molecule to dispersion forces of another molecule, we could compare them because the one that has more electrons or higher molar mass is going to have higher dispersion forces. Okay, so that's our weakest intermolecular force. Next, I'm going to go to our next strongest, which is called dipole-dipole. Okay, dipole-dipole intermolecular force is between 2 polar molecules. Okay. A polar molecule is a molecule that has a permanent positive side and negative side. Okay. This comes from chapter 9 in Gen Chem 1. Okay, so something like HCl. That molecule has a hydrogen on one side and a chlorine on the other. Now, if we look at the periodic table, atoms are more electronegative the more we go to the right and up, making fluorine the most electronegative element on the periodic table. So between hydrogen and chlorine, following the trend that as you go right and up, they get more electronegative. Chlorine is more electronegative. Okay. So my arrow, what that's showing is that the electrons are shifted towards the chlorine. Another way to say that is it's got a partial positive and a partial negative side. Now, unlike the helium example I just did, HCl always has, hydrogen's always the positive end, and chlorine's always the negative end. So it's like a magnet, like a constant magnet. Okay. Well, if I have another HCl molecule hanging out, next to it with its positive end and its negative end, well, opposites attract, right? So the negative end of one HCl is going to be attracted to the positive end of another HCl. That is the dipole-dipole force. Okay, so it only happens between two polar molecules, and two polar molecules, a polar molecule is one that has a permanent positive end or negative end. Okay, so if something has dipole-dipole, it also has dispersion because everything has dispersion. Now, before we move on, I'm going to summarize a quick way to, like a quick summary of chapter 9 on telling if a molecule is polar or nonpolar. So nonpolar is when it doesn't have a positive or negative side. It's evenly distributed, so there's no plus or minus end. It's not a magnet. Okay. I actually have a set of rules that'll help with nonpolar. So if a molecule is nonpolar, one of these things is true. Step 1. It is made, so molecule is only one element. Example, Cl2, P4, S8, I2. So Cl2, the only element in there is chlorine. Yeah, there's 2 of them, but they're the same. P4, there's 4 atoms, but they're all phosphorus. S8, there's 8 atoms, but they're all sulfur. They're all the same element. That's automatically nonpolar. Because who's more electronegative, fluorine or chlorine? Well, they're the same. So neither one's going to be the minus end or the positive end because they're both the same. Okay. Secondly, if a molecule is made of carbon atoms and hydrogen atoms only. So for example, C3H8, C6H6, or even something like CH3, CH2, 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 CH3. The only atoms I see are carbon and hydrogen. Okay, those are the 2 easiest ones to determine if something is non-polar. Step 3. Let's see, which one do I want to do next? If the central, so you draw the Lewis structure. I'll start with, we have to draw the Lewis structure. So like the picture that I drew up there with lines connecting the atoms. If you draw the Lewis structure and the central atom has only bonds, there's no lone pairs around it, and all the outside atoms are the same element. I'm going to put my example over here on the side. So carbon's in the center. It only has bonds around it. There's only lines around it. And all the outside atoms are the same element. That's automatically non-polar. I don't care how many bonds it has. Or not this, but let's, if I said, if it has all bonds, all of them are the same outside atoms, it's automatically nonpolar. The 4th scenario is you draw the Lewis structure. And all the polarity arrows, which are like that, cancel out. So for more details on this, I'm going to send you back to chapter 9, and I'll be happy to give you links to those videos if you want. So if something follows one of these 4 rules, that makes the molecule non-polar. If something does not follow any of these 4 rules, it meets none of these criteria, then it's automatically polar. Okay. So that's how you can tell if it has dipole-dipole forces. I have 2 more intermolecular forces to do. What colors did I do in the last? Oh. Green, red. Okay. Make that blue. The next strongest one after dipole-dipole is hydrogen bonding. This one's super duper specific. So it is between two molecules that each have at least one of these bonds. And these bonds are fluorine bonded to hydrogen, oxygen bonded to hydrogen, or nitrogen bonded to hydrogen. So you have two molecules, and both molecules have at least one of those three bonds. And it has to be specifically not that it has a nitrogen and a hydrogen, but that they have a hydrogen attached to the nitrogen. So, like if I draw you a picture like this, and say I have these two molecules. I know they're not the same, but they have two molecules. And if I want to tell if they have hydrogen bonding, well, you look at the two molecules. And you look at each of them, and you're looking for these three bonds. Well, this molecule has an NH bond. It also has CH bonds. I don't care. But it has at least one NH bond. And then H2O has at least one OH bond. It actually has two of them. So that's going to give it hydrogen bonding. What happens are hydrogen bonding. These three bonds are the most polar of all the bonds. So they're like dipole-dipole forces on steroids. They're like extra strong dipole-dipole. Okay. That's what hydrogen bonding forces are. Okay. If something is hydrogen bonding, it automatically also has dipole-dipole and dispersion, because everything has dispersion. Okay. The last one, crap, I already forgot what colors I've done. I think it's an orange, is ion dipole. This is the strongest one. Ion dipole is between an ion, something that has a permanent charge, Na+, Cl-, NO3-, something that's an ion, and a polar molecule. This happens when we make solutions a lot. When I take like sodium chloride, which is made up of sodium ion, and water. Well, water is polar. It's got a negative end and a positive end. So that ion is attracted to the negative end of the water. And so all these waters would surround it. Now, if I have chloride, we would see the chloride attach itself to the hydrogen end of the water because opposites attract. Okay. So, depending on the solute-solute bonds you have to break, the stronger the forces, the more energy that's going to take, the bigger the up arrow is. And the solvent-solvent, the stronger the forces between them, the bigger the up arrow. And then the solute-solvent, the stronger the forces, the bigger the down arrow. That's playing a role into this and this and this, which all decide whether or not a molecule happens. So a solution happens, sorry. Stronger forces, the solute and solvents that have stronger forces between them, that's more likely to make a solution, to evenly mix with each other, because they're very attracted to each other, so they're going to easily work well together. Okay. So, recapping. Exothermic processes, delta H is less than 0, tend to make spontaneous mixtures. Things that have an increase in disorder, so delta S being positive, tend to happen spontaneously, so tend to make mixtures. And the stronger the intermolecular attractions we have between the solute and the solvent, that tends to make them happen spontaneously as well, so evenly mix. So these are the three scenarios we have to look at if we're trying to decide, hey, if I take this and mix them together, are they going to mix? Those are the three situations we have to look at. Okay, so just pointing it out while we're talking about this, we're talking about making a solution, which is not a chemical reaction. We're just mixing stuff together. Chemical reactions sometimes look like you're making a solution, but they're actually chemical reactions. So you have to be careful that in chapter 13, we're not doing a chemical reaction. We're mixing sugar and water, or salt and water, or sugar and salt and water, or naphthalene and gasoline. We're mixing things together, but they're not reacting. Okay, so we're not talking about chemical reactions here. So the last thing in our little background part 1 video is looking at crystallization. So Well, actually, it's looking at the different types of solutions. So when I take sugar and water, and I've already decided that they make a solution, they make a homogeneous mixture. Um, every time I mix sugar and water together, they're not automatically the exact same solutions, because I can put different amounts of sugar and water in there. And later in the chapter, we're going to get to calculating that. But terminology wise, so when I'm at a restaurant and I want sweet tea, and they don't have sweet tea, they have unsweetened tea. So they bring me unsweetened tea and in the little, black box that has the little sugar packets in it. And I just take regular sugar out and I pour it in and I mix it up with my straw. I can never get my unsweetened tea that I'm trying to make sweet tea to be as sweet as the tea that I make at home. When I can keep pouring sugar in, I can pour sugar in as much as I want, and I stir and I stir and I stir, but at the bottom of the cup, sugar is going to sit there. Okay. When I'm mixing things together that I know do mix, they do make a solution. But when I try to keep mixing them more, they no longer mix. Like the sugar sits at the bottom, it's no longer mixing with the water. That is a saturated solution. So a saturated solution is as full as it can get. You can no longer make more of that mixture. It's full. Okay. Now, with my example with the unsweetened tea, the biggest issue there isn't is actually temperature. There's ice cubes in there, so it's cold, and the saturation limit of cold water and sugar is not very high. So like it doesn't take very much sugar to get to that limit. If I do it at room temperature or even above room temperature, because when I brew my tea and it's nice and warm, I can get more sugar dissolved. Okay, so saturated solution, it's full. Every solution, like every time I mix sugar and water, other than when it's full, below that, it's unsaturated. That means I could mix more sugar with it. So an unsaturated solution is not yet full of the solute. Okay, so most of the solutions you come across on a daily basis are unsaturated because you could add more stuff and it would still continue to mix. Okay, so when we're talking about solubility right now, what I mean, when I'm thinking about like taking a solute and mixing it with another solute, I'm kind of going with a yes or no here. Yes, they're going to mix, or no, they're not. Well, every mixture, every two substances that I try to mix together have an actual solubility limit, and that's that saturated spot, okay? And that's based on temperature. So sodium chloride in water has a certain amount of sodium chloride that I could add to 100 milliliters of water to get to the saturation limit. And that's different at 12 degrees Celsius than it is at 25 degrees Celsius than it is at 85 degrees Celsius. So there's an actual number that goes with all of this. Right now, I'm not focused on us knowing that number. We're going to come back and deal with that later this semester. But knowing that that number, that's the solubility, is the saturated point. And everything less than that is unsaturated. Now, you would think saturated, unsaturated covers everything. Saturated when it's full, unsaturated when it's less than full. But oh no, buddies, there's one more, and it's the best one. And it's called supersaturated. It's the best because it has the word super in it and because it's fun to play with. So supersaturated solutions are mixtures where we have more solute dissolved than the saturation limit. So we're above the saturation limit. Like, wait a second, lady. Saturation limit is the limit, right? That's how much you can mix. Remember the other part of the saturation limit was temperature. So we can trick a solution. So to make a supersaturated solution, what we need to do. So in this picture, it's water and sodium acetate. Sodium acetate is the solute and water is the solvent. What they did was they took a beaker of water, warmed it up to like 80 degrees Celsius, and then poured in sodium acetate. Poured in a lot of sodium acetate. Didn't quite get it to the saturation limit at 80 degrees Celsius, but poured in almost the saturation limit at 80 degrees Celsius. And they took it off the hot plate and let it slowly cool to room temperature. So it started out at 80 degrees Celsius, and we almost got it saturated at 80 degrees Celsius. And then I set it down on the counter, let it cool to room temperature, and once it's at room temperature, well, there's more sodium acetate dissolved in water at room temperature than there should be, because at room temperature, the saturation limit is way lower. But it's still dissolved because I dissolved it when it was warmer and then let it cool. Okay. What's fun is to mess with them. Supersaturated solutions are super unstable because they're not supposed to be there. It's above the limit, right? So here they're dropping this tiny little crystal of sodium acetate, like one more chunk. And what looks like is happening here is it's like the beaker is breaking. It's not. What's happening is the water and the sodium acetate, which look just like water, is crystallizing. It's turning into a solid. So by the end, here, it would be a full-on solid. So you know, like at Dairy Queen when they used to turn your Blizzard upside down, you could take this super saturated solution in step 3 here and turn it upside down. It would be a solid. Even the water is part of the solid now. And what also is fun is it gets really hot when this happens. It releases heat. Okay, so super saturated solutions are just super fun to play with. What I like to do is I start with like step 1 here, and then instead of dropping something into it, I take my beaker and I pour the liquid out. And when I pour it out, when it hits the counter, it crystallizes. It does this, okay? And then I kind of just keep pouring and I build myself like a little house or like a little castle, or I write my name or something. And what's also fun is if you're at step 3 and you want to go back to step 1, all you got to do is heat it back up again, warm it back up to its 80 degrees or wherever it was when you made the solution. It'll go from its solid back to its aqueous solution, and then you can just repeat this over and over again. So I think they're super fun. Some magicians use this, actually. They call it hot ice. So if you go to YouTube and you Google hot ice, what they do is they pour this super saturated solution into ice cube trays because it looks and acts just like water. And sodium acetate's the best one to use it with. And then when you touch it with your finger, that's going to set off the same thing. So here, doesn't this look like ice? So, and it also lets off heat. So when you touch it with your finger, it looks like you're freezing water with magic when it's super saturated solutions. So those are fun. Oops, I didn't mean to do that. But those are fun definitions. Oh, yep. Okay, this is the super classy way to end this video. So fun definitions in chapter 13. We've got more videos to come.